Greetings and salutations, magical chemists. Today we're going to talk about collision theory, which is a model that explains reaction rates. Collision theory, just like its name suggests, is based on the reality that for a given reaction to occur, molecules must collide. In fact, the rate of a reaction is directly proportional to the rate of reactant collisions. Now, the collision of reactants that actually results in products has a special name. It's called an effective collision. And there are two conditions that must be met for this to happen. First, the molecules have to collide in the correct orientation. That just means that the atoms that are going to form new bonds have to bump into each other. And the collision must occur with sufficient energy. The molecules have to collide hard enough to overcome the activation energy of the reaction. Let's take a look at both of these conditions in a little more detail. Okay, correct orientation. As we stated, the reacting species must collide in an orientation that allows contact between the atoms that are going to become bonded together. Hopefully that makes sense. This can even be calculated mathematically as something called the orientation factor, which represents the fraction of collisions that occur with an orientation that allow the reaction to happen. So, the higher your orientation factor, the higher the probability that a given collision will be an effective collision. Let's take a look at an example single replacement reaction. In this reaction, initially, A is all by itself and B and X are bonded. But, oh no, B and X break up. Now A and X are bonded and B is all alone. Well, hopefully it should be obvious that for this to happen, if you're forming a bond between A and X, whatever those are, A and X have to bump into each other. So if A bumps into B, well, doesn't matter. Nothing's going to happen because that's not giving us the orientation we need. But if A bumps into X, that's the chemistry we're talking about. As you know, AP Chemistry, the exam, is very fond of particulate representations, so you can definitely be expected to look at pictures of reactions and figure out which one would be the best possible orientation. In that case, you're always looking for the same thing. The atoms that are going to form new bonds need to bump into each other. Okay, so orientation is one factor to have an effective collision, but it is not enough. If the atoms that are going to bump into each other, but they don't have enough energy to overcome the activation energy, you still don't have an effective collision. So basically, activation energy is the push that you need to start a reaction. Why do you need a push to start a reaction? Well, the idea is the collision has to occur with enough energy to overcome the pre-existing attractions or the pre-existing chemical bonds. That's the activation energy. Activation energy is so important, it even has its own variable, E sub A. Okay, here is a super important statement that you absolutely have to ingrain into your brain. So whatever you need to do to this sentence to make it stand out in your notes, do so now. The idea is the higher the activation energy, or the higher the energy barrier, the slower the rate of reaction. And yes, this is so important, I gave it its own rainbow. Hopefully it makes sense. To have an effective collision, you have to collide with enough energy to overcome the activation energy. If you have a high activation energy, you have to collide with more force, so a lower percentage of collisions will collide with sufficient energy. Now, there's something at the top of the activation energy. It's called the transition state. This is the highest energy part of the reaction because it's this weird transient state where some bonds are partially broken and some bonds are partially formed, and it is not a happy place. It is unstable, which is why it's so high energy. In this activated complex or transition state, the bonds that are breaking or forming are shown as dotted lines. In the example reaction, we've got H2 and F2. Right? They're just two diatomics with single bonds. So they started off with a single bond between hydrogen and a single bond between fluorine. But those have to break and new bonds have to form. So that's our dotted line. Honestly, I would claim this should be a dotted line as well. But, you know. It is important that you can look at a potential energy graph and calculate the activation energy, or at least identify it, because for in this example, there are no numbers. So the activation energy of the forward reaction is the height from the reactants up to the top of the bump. But you can also calculate the activation energy of the reverse reaction by combining that total distance, right, that height of that bump, and you also have to take negative the delta H. You might be thinking, wait, negative? Well, yeah, because you need to add the absolute value of the distance here, right? Because this is a negative delta H, the system released energy. But if you subtract 268, you're going to make it look like it was a smaller activation energy in reverse. So that's why you have to flip the sign when you're combining them to get the activation energy of the reverse reaction. Okay, now we know the basics of collision theory. So let's take a look at the effect of temperature on the percentage of effective collisions. Temperature, of course, is a measure of the average kinetic energy of a sample. So as temperature goes up, by definition, the average kinetic energy of the particles, on average, also increases. So there's a quick phrase to remember this. Heat 'em up, speed 'em up. And it is important to recognize that a higher temperature will cause a higher reaction rate for two specific reasons. First, because the particles are moving faster. Well, they're moving faster, so there's just going to be more total collisions overall. But not just that. Because they're moving faster on average, that means, on average, there will be higher energy collisions. So, a greater percentage of your collisions will have enough energy to overcome the activation energy. You can represent this using a classic Maxwell-Boltzmann distribution. On the graph, T1 is showing you the energy distribution of all the particles in the sample at a lower temperature. And remember, it's always an average, so some are moving faster, some have more energy, some have less energy. But as you can tell, only a very small amount here will actually have enough energy that if they collided, they could overcome the activation energy. But when you heat them up and speed them up, let's look at the change in the graph. Once again, you still have a distribution of energies. However, the higher the energy on average, the broader the distribution. And of course, the average is further to the right. So now, oops, that's not the color. You will have a higher percentage of the moving particles are basically moving with enough energy so when they collide, they would overcome the activation energy. However, please make note of this fact. Increasing the temperature does not decrease the activation energy. The activation energy remains the same. Only a catalyst can decrease activation energy. And I promise there will be more on that to come, but not in this video. Okay, that's the basics of collision theory, but let's take a moment to kind of summarize and clarify some things that we talked about. There is an important distinction between changes to a reaction that will change the rate of the reaction, like make it go faster or slower, versus changes that can actually change the rate constant K. There are only two things that can change the rate constant. If you want to increase the rate constant K, you can either increase the temperature or lower the activation energy by using a catalyst. And of course, to decrease the rate constant, you do the opposite. Now, the rate of a reaction can be changed by lots of things, because that's just measuring the change in concentration of your reactants or products over time, right? So, of course, increasing the temperature, lowering the activation energy, that'll give you a higher reaction rate. But having weaker reactant bonds, or a high orientation factor, or a high concentration of reactants, all of those things would increase your reactant rate. And the reverse of those things would give you a lower rate of reaction. Okay, now let's look at collision theory in a nutshell, because collision theory is the heart of kinetics. It explains all the stuff about reaction rates that we've been talking about this whole time. Collision theory states that, well, just like the name suggests, if you want to have an effective collision, your particles must collide, and when they collide, they must have sufficient energy and in the correct orientation. Collision theory is what you use to explain your answers. You know, those lovely justify your answer on free response. Well, why would increasing the concentration of reactant particles increase the reactant rate? Well, more particles means more collisions, thus more opportunity for effective collisions. Increasing the kinetic energy, you know, the temperature, heat them up, speed them up. Well, the particles are moving faster, so they collide more often and with greater force. And increasing the pressure for gases is basically increasing their concentration because the particles are closer together and therefore more likely to collide. And there you have it. That's collision theory. I hope it was a smashing success. Thank you for playing with the glories of chemistry.